Good morning everyone. I'm here again with a video of solid state for class 12 students, and my today's topic is close packing in crystal lattice. Okay, close packing in crystal lattice. So let's proceed. First, we have to know what does it mean, close packing in crystal lattice. As you know that in crystal lattice there are various constituent particles and they are always packed in a regular arrangement. Now, closely packed or close packed means in this arrangement the maximum available space is occupied, leaving minimum vacant space. Here, try to understand this. Closely packed arrangement means the maximum available space is occupied and minimum space is vacant. As you know that in crystal lattice the constituent particles are occupying the space. So here the constituent particles will occupy the maximum available space and minimum space will be vacant. That means close packed or closely packed structure. So it corresponds to a state of maximum possible density, of course, because the maximum space will be occupied by the particles. And the greater the close packing, greater will be the stability. Okay, the closer the packing, the greater is the stability of the packed system. Am I clear? What does it mean? Close packed structure. That means in this arrangement maximum available space is occupied by the constituent particles and minimum space is vacant. So let's see this. Close packing in one dimension. Though here we are considering the three-dimensional crystal lattice, but initially we should start thinking from one dimension. Then it becomes easier to visualize or to imagine. So close packing in one dimension, there is no another way out. You see, if you have to pack the spherical atoms or molecules or ions, then there is no other way out. Horizontally, you have to keep them in a line touching each other. So this is the close packing in one dimension. Now I am coming to the close packing of two dimension. You see, in case of close packing of two dimension, you have two possible ways. One is this one, where each line is similar. You see, this one and the next one, these two are similar. If you keep them similar, that is one type of arrangement. As all the lines are similar, so you can consider this as AAA type. AAA type, that means all the lines are equal, and this gives you square close packing. This gives you square close packing. Now another option is, if you keep the first line in this way, the second line you can keep in another way. See, this is also close packing. This is also close packing. Okay, but this first line is not similar with the second one. Okay, and again it is another one. So you can consider, you can write this as AB type. Okay, the name of this is hexagonal close packing. Why is it hexagonal and why is it square? Because you see, in between, if you consider each atom, this is the atom, suppose each atom is in contact with 4 another atom. Each atom is in contact with 4 another atoms, so it is square close packing. But here each atom is in contact with 6 other atoms. 1, 2, this 3, this 4, this 5 and this 6. As it is in contact with 6 other atoms, so the name of this is hexagonal close packing. So you see, if you consider the close packing in one dimension, there is no other option, only one option. But if you consider the close packing in 2 dimensions, you can get 2 types of arrangement. One is square close packing, another one is hexagonal close packing. Now in this context, we will know about a new term, that is coordination number. Coordination number. What is it? The number of nearest neighbors of a particle is called its coordination number. You see here, every time I am using the term particle because it may be atom, it may be ion or molecule, anything. So here the particle, the number of nearest neighbors of the particle is called its coordination number. So here in one dimension the coordination number is 2 because each atom is in immediate contact of 2 other atoms. Okay. Here in square close packing coordination number is 4 and in hexagonal close packing coordination number is 6. I hope it is clear. Coordination number. Now one dimension we have understood, we have seen, then 2 dimensional close packing. Now obviously the 3 dimensional close packing, which is the actual one. 3 dimensional close packing. Now you see, if you have to consider the 3 dimensional close packing, then you have 2 ways, 2 options in 2 dimensional close packing. So from this square close packing you will get one 3 dimensional packing, and from hexagonal close packing also you will get another 3 dimensional close packing. Got it? In one dimensional one option, but whenever you are coming in 2 dimension you have 2 options. So if you go for 3 dimension, then this will give you one 3 dimensional close packing, this will give you another 3 dimensional close packing. Got it? So first I am considering the 3 dimensional close packing, which we will get from the square close packing. Okay. See, that is why I have written here 3 dimensional close packing from 2 dimensional square close packed layers. So from here, so if 2 dimensionally here you have the square close packing, so again there is no another way out because you have to stack the other one. The first layer is packed, square close packed. Now whenever you are putting another layers, there is no other option except the same one. Okay, so same one here. So the first layer, second layer, third layer, fourth layer, fifth layer, all other layers are exactly same. So you can consider this as AAA type. A means the first layer, then the second layer, then the third layer, all are similar. That is why AAA type. And this gives you simple cubic packing. That is this kind of structure. Simple cubic packing, this kind of structure. Okay. Now what? Now we will consider, so this one is done, this one is done. That means we have to come to this one, hexagonal close packing. Hexagonal close packing in 2 dimensional. Now you will stack another layer over it. Okay. So the next one, that is 3 dimensional close packing from 2 dimensional hexagonal close packed layer. See this carefully. This is very important part to understand. This should be very much clear to you. This is the hexagonal close packed structure in 2 dimension. Now you have to stack another layer over it. Okay, you have to stack another layer over it. Whenever you are stacking another layer over it, you see the first layer is the blue balls and the second layer is the yellow balls. So when you are stacking another layer over it, then you are getting two types of voids. Okay, you are getting two types of voids. One is octahedral void, another one is tetrahedral void. What does it mean? Void means the free space. You can imagine that whenever you are stacking these spherical balls, that means the particles, you see there you are getting some vacant space. Initially we have learned this, that maximum space will be occupied but minimum space will be left. Okay, free, empty. So you see in the two-dimensional layer also you are getting few void. Now when you are stacking another layer, then also you will get few voids or holes. So there you will get two types of holes, octahedral and tetrahedral. Let's see this. Okay, this is the figure, and if you get a clear picture of this, octahedral and tetrahedral voids. You see this one, the light red color layer is the first layer, and then the deep red color one is the second layer. So when you are putting this, you see this is a type of void which is known as tetrahedral void. Tetrahedral void means one is one atom in one layer, and above that three other atoms. One atom, you see the light red color one atom in the layer, in one layer, and in another layer there are three atoms. You see the red color one, deep red color one, 1, 2, 3. So when you have one sphere in first layer and above it three spheres, then between these two layers there is a void created, that is known as tetrahedral void. Okay, but you see here in octahedral, what happens here? In the first layer, or I'm coming here, you see here in the first layer, the light red color one, first sphere, second sphere and third sphere, which is making a triangle, and then above that the deep color one, the deep red color one, the first one and second one and third one. So in the first layer there are three spheres, and in another layer also there are three spheres, but these two triangles are inverted. These two triangles are inverted. Then you see you are getting a star like this one, this type of void, and this void is known as octahedral void. Okay, there are two types of void created when we stack another layer over a hexagonal close packed layer. We get two types of voids. One is tetrahedral, another one is octahedral. See this once again in separate pictures. First, this void, definition of this void. In the close packing of spheres, certain hollows or voids are left vacant. These holes or voids in the crystals are called interstitial voids or sites. Interstitial voids or interstitial sites. Interstitial means in between the lattice. Now, two important interstitial voids are tetrahedral void and octahedral void. See this once again. Tetrahedral void. That means one, you can consider the one sphere in the upper layer or the below layer. Anyone. Main thing is in one layer one ball, and in another layer three balls or spheres. So this void which will be formed here, when this will come in immediate contact of this, so this three spheres and this one sphere, the void created between these all is known as tetrahedral void. Okay, the geometry of tetrahedral is like this. Okay, so this is tetrahedral voids. Now in octahedral, what happens here? In first layer, three spheres like this yellow one, three spheres, they're making a triangle like shape, and in another layer again this three blue balls, they are making another, they are making another triangle, but these two are inverted. These two triangles are inverted. In this case, between these six, among these six spheres, the void which is created, that is octahedral void. You see here, these three, and these three. So the void created among these six, that is known as octahedral voids. Am I clear? So try to understand. In case of simple cubic lattice, all the layers were equal, but all the layers were equal. You consider this one, all the layers were equal. But in case of this, when you are stacking the second layer over the first layer, then you are getting two types of voids. One is octahedral void, another one is tetrahedral void. Now to continue the three-dimensional crystal lattice, you have to stack the third layer over it. Am I clear? The first layer is this hexagonal closed packed structure, and then whenever you are stacking the second layer, then you are getting two types of voids. One is tetrahedral void, another one is octahedral void. Now when you will stack the third layer over it, then you have two options. Got it? First layer, second layer, clear. Two types of voids, clear. Now when you are stacking the third layer over it, then you have two options. When you will place the spheres here, you can cover the octahedral voids as well as you can cover the tetrahedral void. Am I clear? The first layer is this hexagonal closed packing. Whenever you are stacking the second layer, you are getting two types of void, octahedral voids and tetrahedral voids. Now when you will stack the third layer, then you have two options. Either you can cover all the octahedral voids or you can cover all the tetrahedral voids. Got it? I am coming to those pictures. You see this one? Here I have compared these two together, tetrahedral voids and octahedral voids. I have discussed these two. I hope these are clear now. Now I am coming to this three-dimensional figure. So when you form the three-dimensional closed packing from two-dimensional hexagonal closed pack layers, you have two alternatives. One is covering the tetrahedral voids, another one is covering the octahedral voids. Come to this. If you want to cover the tetrahedral voids, it is found that the third layer has to be exactly equal with the first layer. First layer is this. If you are putting the second layer, then you are getting tetrahedral voids and octahedral voids together. If you want to cover the tetrahedral voids, then you have to stack the spheres exactly same like the first layer, and you will get this kind of structure. Which is known as hexagonal closed packed structure, HCP. In the next slide you will get the full name is written. Here I have written the shorter name HCP, and in short it is always written in small letters HCP, that is hexagonal closed packed arrangement of spheres. That means here the first layer and the third layer, these two will be same. That is why you can write this as ABA type of arrangement or hexagonal closed packed arrangement. Okay, where we want to cover the tetrahedral void. Now the next one, if you want to cover the octahedral void. If you want to cover the octahedral void, then it is found that the third layer is different from both the second layer and first layer. But the fourth layer is exactly same with the first layer. Fourth layer is exactly same with the first layer. So you can consider this as ABC type of arrangement or CCP arrangement, that is cubic close packed arrangement of spheres. Okay, cubic close packed arrangement of sphere. Got it? That means if in two dimensional it is square packing, from there you are getting simple cubic. If the in two dimensional it is hexagonal packing, from here we are getting two types of voids, octahedral void and tetrahedral void. If you want to cover the tetrahedral void, you are getting HCP structure, hexagonal close packed structure, and if you want to cover the tetrahedral void, you are getting cubic close packed structure. And you see this figure CCP structure is nothing but the FCC type of crystal. Okay, this is nothing but the FCC type of crystal. Cubic close packed CCP arrangement is equal with the FCC type of crystal, and this is ABC type of arrangement. See this once again, there should not be any kind of confusion. In case of hexagonal close pack or HCP structure, it is AB type of structure, and in cubic close pack, here I have written cubic close pack, here I have written FCC, both are same thing. Here it is ABC type of structure. You may get various types of figures in references. Don't become confused. If the layers are AB type, it is hexagonal or HCP. If the layers are ABC, it is cubic close pack or face centered cubic structure. Okay, see this once again, in hexagonal and in cubic close pack, the two dimensional figures are same. In two dimensional they are hexagonal close pack, and then you are stacking the second layer. These two are also the same, forming both the voids, tetrahedral voids and octahedral voids. When you are putting the third layer, then there are two options and two different structures will form. The first layer and the second layers are identical, but in case of third layer, if they are same AB type, that is HCP covering the tetrahedral void, and if the third one is different, that is ABC covering the octahedral void, they are cubic close packed structure. Okay, so we learned three types of, one is simple cubic one, another one HCP, and the last one is CCP type of structures. Now one more thing, that is number of voids. Number of voids. This is an information and it is important for 1 mark question for your exam. That is number of octahedral and tetrahedral voids in a close packed structure. If in a close packed structure there are n number of spheres, if in a close packed structure there are n number of spheres, then total number of tetrahedral voids will be 2n, total number of octahedral voids will be n, and the total number of voids will be 3n. So this is important for 1 mark question. If there are n spheres in a close packed structure, then there are 2n number of tetrahedral voids and n number of octahedral voids. Another information for 1 mark question, that is coordination number. You all have already learned what is coordination number. So in HCP, hexagonal close packing, and in CCP, cubic close packing or FCC arrangement, the coordination number of a sphere is 12. Try to understand this. How is it so? Here I have given both the structures, HCP and CCP or FCC. You see, if you see this atom, if you see this atom or this atom in the same plane, this atom is in immediate contact of 6 other atoms in the same plane. 1, 2, 3, 4, 5 and then 6. Got it? 6 atoms in the same plane. 3 atoms in this plane and 3 atoms in this plane. So as a whole, this particular atom is in immediate contact with total 12 atoms or total 12 spheres or total 12 particles. 6 in the same plane, 3 in the above plane and 3 in the below plane. So the coordination number of both type of arrangement, HCP or CCP, that is 12. Okay, I hope these 3 types of close packing are very much clear to you. I am repeating this again from the very beginning, that in one dimension you have no other option, you have only one option, this one, and in 2 dimension you have 2 options of these 2, and in 3 dimension from here you will get only this one simple cubic packing, and from this hexagonal close packing you have 2 voids, octahedral void and tetrahedral void, these 2, and if you want to cover the tetrahedral void you are getting HCP structure. If you want to cover the octahedral void you are getting CCP structure. So I hope you have understood these things. Listen this carefully, see this video again and again, so that this should be very much clear, because for the next topic these all packing should be very much clear in your view. Till then, be safe, stay at home. Thank you.